Peter, do you know how to use eigenvectors to solve this linear system of ODEs?
Oh, I know this. Just put it in a calculator. Boom, solved.
No, you imbecile. Let me show you. Let's first put our system of equations in matrix vector form. X prime is the vector of the first derivatives, A is the coefficients matrix, and X is the vector of the original functions.
Okay, I'm following. So we need to find the set of all solutions X in CRR3 that satisfy this system.
Right, so let's call that set of solutions as S. Our problem now boils down to finding a closed form for S. Now obviously we know S is a subset of CRR3.
Yeah, that makes sense. The solution set is a subset of all possible inputs.
But the important idea here is that S is not just a subset, it's also a subspace.
Wait, why does that matter?
Because if S is a subspace, then it has a basis. If we can find that basis, then we can express every element in S as a linear combination of that basis. So now, the problem has reduced to just finding enough solutions to form a basis for S.
Oh, that makes sense. But how many solutions is enough to form a basis? We need to know the dimension of S for that, right?
Yes. In general, S has dimension n if it's a subset of CRRn. This is provable by constructing a linear isomorphism between S and Rn.
Okay, I see. So for n functions in the system, we need to find n independent elements in S to form a basis.
Correct. Let's find the n basis functions then. Say our basis is composed of n functions, f1 through fn. Recall that by definition of being a basis, these functions must satisfy two conditions. First, each function f must be an S, so it must satisfy f prime equals a times f. Second, all functions must be linearly independent.
It still seems like a pretty hard problem, though. How do you do that?
Let's look closer at the first condition. You might notice that f prime equals a times f looks almost identical to the classic setup of y prime equals k times y for some scalar k, where we'd make y some exponential function.
All right, I remember that. But A is a matrix, not a scalar, so that's useless?
No. We just have to make A act like a scalar, and A acts like a scalar when applied to an eigenvector. So if we make f output eigenvectors, then A times f turns into lambda times f. So f prime equals lambda times f.
Oh, that's clever. So we can just make f be an exponential function with an eigenvector factor.
Precisely. So for an eigenvector v and its eigenvalue lambda, we define its corresponding basis function to be f equals e to the lambda t times v.
Wait, but that only solves the first condition. What about the second one? The functions are in S, but are they linearly independent?
If A has n independent eigenvectors, then yes, they are. The functions point in eigenvector direction, so they're linearly independent. You can evaluate at t equals 0, for example, to prove it.
Oh, wow. So we knocked out both conditions just by using eigenvectors as a solution to satisfy the first condition.
In the end, each basis function is an eigenvector exponential, and each solution x in S can be represented as a linear combination of this basis.
So to find all solutions to the system of ODEs, you just find a basis for the solution set consisting of exponential eigenvectors?
Yes, follow for more. Peter, today we're going to calculate your excess belly fat using integral calculus.
Whoa, Stewie, I don't remember looking that fat. That's gotta just be a bad photo, right?
No, that's definitely how you actually look. First, let's isolate the excess belly fat. We'll draw a cutoff line where your belly should be, and everything above it is colored in red.
Okay, geez, man, no need to rub it in with the graphic.
Cleaning the image up, here's what the boundary of your excess belly looks like. Now, let's fit a polynomial on it. This polynomial tells us the distance your belly extrudes at any point.
Wow, you need a degree 7 polynomial to describe it. I guess I'm pretty special.
Let's also assume that your belly has semicircle cross-sections.
I guess I am pretty round and circular, too.
So the polynomial gives us the radius of the semicircles at any point. Now, time to integrate. Take the integral from x equals 0 to x equals 2.085 using semicircles where the radius of each semicircle is described by the polynomial. The volume comes out to be 2.01 cubic units. Scale that to your height of 6'1" and you'll get that you have about 133 extra pounds of belly fat.
Holy cow, Stewie! That can't be true, right? That's horrific.
Well, we probably overestimated by using semicircles to estimate the cross-section of your belly. But that number is in the right ballpark.